Yeah.
Okay, it's recording. So for Joseph, for Daniel, for the rest of the Institute who's following along remotely or via YouTube, um, welcome to the Active Inference Institute. We do a weekly textbook group readings twice on Thursdays, once in the morning, once in the evening, if you're roughly in the Western Hemisphere. And yeah, so today we're going over chapter 7 in cohort 7. And we'll be talking about essentially the exemplar discrete state space models and active inference. That would be hidden Markov models and partially observable Markov decision-making processes. We have a nice T-maze example, which is pretty classic in the field as well as in kind of behavioral and neuroscience and neuroimaging studies in general. And again, we're in the second half or part two of the book, which is highly dedicated to constructing essentially active inference models, as opposed to part one, which is much more focused on theory and definitions. Um, and so it's for anyone who's interested in computational modeling, whether it be doing it themselves or getting a clearer grasp of kind of what are these computational models or cognitive models that we're putting together in order to, say, collaborate with a team of people who do cognitive modeling, then it's very worthwhile to spend time with the second half of the book. And then furthermore, there are many discrete state spaces in a very general sense, in a physical sense, in a kind of decision making and human belief sense. It's referring to scenarios where essentially, if we think about it in data, it's sort of like categories. It's thinking about binaries. It's not so much thinking about fully continuous number series, such as a range over 1 through 1 million, where we could have so many different values, including with the decimal points, potentially an infinite number of values. Instead, we're looking at, say, RGB color scales on old television, so red, blue, green. We could have a distribution between the three of them in the sense of how much red, how much blue, and how much green. But nonetheless, it's a kind of discrete categorization process. So um, yeah, normally I give a rather long kind of chapter summary, but I'm happy to just kind of open up the floor if Joseph, you have any particular questions or things you'd like to discuss here.
I would like to hear your summary. I also
Okay.
do have some questions. I haven't fully been able to understand, for example, figure 7.2. So if
Hmm.
we could, like, I guess I just don't understand what's plotted and where the lines are coming from. But yeah, I'm very interested in trying to build these models and understand how to build them, and so this seems like a really critical chapter for me.
Yeah. Yeah, no, that's great. Yeah, figure 7 too, which I personally have not spent a lot of time with recently. So coming back to it is rather interesting. Yeah, so this is where the chapter essentially opens with hidden Markov models before we jump up to partially observable Markov decision-making processes. So it's like we have, I believe is my screen still being shared appropriately, or can you not see anything?
No, I don't see your screen.
Okay, got it. Thanks for that. Just realized I'm doing a little bit of display gymnastics. Um, that should have done it. So this is, and a quick reference, this is the coda for the textbook group. And so we have this available to all members, and we have not just a overview of the textbook group and dedicated meetings and time availability and all of those sorts of things for the separate cohorts. We also have a pretty good breakdown of the Active Inference textbook, especially since it became open source. So, so yeah, figure 7.1, I know it's not the one you referenced, but just to make sure we're like familiar with it enough, this is essentially a hidden Markov model. And so understanding kind of the core dynamics here, we also ultimately only have three different components in this model. So we have D, our prior over initial states. It's kind of like what are our beliefs about states whenever we come into a situation, as it were. Um, and then from there, that gets linked to observations that we receive, right? And the relationship between what we believe and sort of what we see is linked through this likelihood matrix A. So it's represented as kind of this broad categorical probability distribution that is conditional observations given our beliefs S or in states S. And then there's also a temporal dynamic over time, right? So we have the B matrix, which is kind of our beliefs about how transitions change from one to another. So that's why we have this sort of state at t minus one to state at t to state t plus one. So it's this temporal dynamic playing out over discrete time steps. Um, and so from there, we can move to 7.2 and a little bit of context. So this is an example that relates to the idea, I believe it's of someone who's playing an instrument and they're trying to actually play a song in accord with the script, the sheet music that they're reading. And so we can quickly imagine a scenario where there's someone who is still learning how to play. This is practice for them. Even if it's someone who's very skilled, they're maybe learning a new piece for like, I don't know, an orchestra performance they'll be doing soon. Um, and so there's all kinds of room for error, right? And to accidentally hit the wrong notes at the wrong time. Maybe you're still on beat, but you know you hit an A rather than an A flat. And so that's sort of what this example is about, is being able to use the dynamics of a hidden Markov model, including what notes play over time, and then also what does the musician believe the note should be versus what we actually hear. Right. And so by being able to like hear, and it's obviously a very kind of abstracted example. There's a lot more to it there. We're not saying anything about what the sheet music looks like, but here we're just simplifying it to saying the musician has a belief about what the note should be versus what they actually observe that they're playing. And so with this figure 7.2, I think the quickest way of kind of getting at what the authors of the textbook are trying to demonstrate for us is sort of an illustrative example is this upper right. This is like beliefs about hidden states. So the agent believes that the first note, uh, in terms of over time, should in fact be the first note, as in it's in row one, so that this row is like its own set of notes. Row two is yet another note. So it could be read as like the top row is A, the second row is A sharp, the next row is B, the next row is C. Not to confuse anyone who's not familiar with scales, but there is no B sharp essentially, unless you're concerned with naturals and all that. So each row is its own note. And then here it's kind of like the musician believes, based on the sheet music, that they should start with the first note, A, and then move to A sharp, move to B, move to C, and then go back to A for the fifth note. So they're just kind of descending a chromatic scale before they get back to A again. That's what they believe should happen. Meanwhile, with our O's or observations, what really happens is that we get an A, we get an A sharp, and then rather than getting the expected B, which is here, the actual observation is that they realize, oh no, they hit the same note twice in a row, which is not correct. But by the fourth time step, they get back to what the note should be. And then here, at time step 5, they also hit the correct note. So kind of what's happening here is that there is at S3, we would say that this is prediction error, right? And so whenever the agent infers their posteriors over hidden states, here they're so conditioned to believe that it should be the right note that they kind of shaded this in as if it's correct. But there's this grayness here. It's so light. But essentially the idea is, this is the note that should have happened. Their observation, however, gives them evidence that it's actually this gray space. This is maybe actually the note that they heard, um, or that they believe really happened. So there are aspects of this that can seem kind of counterintuitive, but really just being able to grasp that the upper right are their beliefs about states. The lower the lower right is the observations they actually receive. And then a good reminder is, in a discrete state space setting, it's like, oh, we're not looking at, the interim between A and A sharp, some kind of microtonal situation. We're just looking at, we're assuming there's A, and then there's A sharp, and then there's B, and then there's C. And ultimately that's the Western scale of 12 notes, in the way that I'm describing the example. So now these graphs on the left are a little more complex. And it will be good to spend a little bit of time with them. I'll first just like read what it says in the textbook. So we'll go with lower left. We're looking at negative free energy gradients or prediction errors, the rate of change of the beliefs in the upper left plot is determined by the value of these errors at each time step. And so what we're seeing, these are negative free energy gradients. In terms of active inference, we're wanting to minimize prediction error. We're wanting to minimize variational free energy. So if these are actually negative gradients, then that means that at each time step, we should actually want these to be rather large, if they're negative. And so the smaller they are, it's kind of like saying that it's sort of the worser scenario. And then that seems to kind of constrain the agent's ability to be confident or kind of understand the situation. So let's see, and then upper left, beliefs, posterior probabilities about each note in the sequence at each time step. Yeah, so these are the posterior probabilities. It's kind of like their ability to understand a particular note here of what it should have been has gone down, right? So there's a kind of constraint there that's been applied. And then once they start to hear the correct notes again, their confidence kind of increases. I will be honest, these two graphs on the left, they're much more rarely used today in active inference, like these specific types. It might be because of the sort of kind of counterintuitive nature, because more often than not, we actually are looking at, the inverse of the situation. So we're looking at positive free energy. And so actually this would look quite bad. It would look like step 3 is actually a rather good thing in terms of minimizing uncertainty, and it's the other way around. But I think that the authors who composed this are really trying to get at a particular kind of point by representing it this way.
Yeah.
Um,
I
yeah,
think I'm still maybe a little lost about. So you said that just focusing on this top left,
yeah.
the y-axis you said is probability. So okay, so I get that. And what are all the different lines? Are these different trials or um,
Yeah, yeah,
and
it's
I
quite
guess
tough. They
one of
don't
the
leave us.
things. Yeah, one of the things I'm really wanting to understand better is how the agent actually is learning, and maybe that comes later on. This is after this example, but where do we adjust the weights of the in these matrices according to the result we get from our minimization step?
Oh yeah. No, that's an excellent question, very relevant. So in this example, they don't actually apply learning at
Okay.
all.
Yeah.
So this is essentially like a static model. Yeah. And I think they're just using it to try and kind of get at the more inference level dynamics as opposed to learning. And so I know that this is pretty familiar terminology for folks who do other forms of kind of computational modeling, data science, deep learning. I heard you say that, referring to it as adjusting the weights, all of that is very relevant here. But so for this particular model, yeah, there is no learning. What could happen is that, to refer to this again, um, this what typically what an agent learns are these kind of probability distributions over time. And so D, your prior beliefs in the Bayesian sense, those could be updated. So you could the agent could effectively learn its D matrix. Um, A could be learned, B could be learned. Actually, any of its parameters, including C and E, which C is just a prior over observations, E is a prior over policies or actions. So that way, that's what's missing from this, and it's also missing from this because we have no policy inference, right? So the HMM is kind of like can be viewed as a truncated version of the POMDP, which is exactly equivalent until we get to here, this connection to pi or representing policies or action. And so an HMM is kind of like perception and no action. Uh, Partially observable Markov decision-making process is perception, and here we have the connection to actions that it can take. So we get these kind of relationships where suddenly state transitions, the B matrix, if you recall earlier, 7.2, the B is simply what is the next state going to be given the current state, whereas here we now have, yeah, we now have what is the next state going to be given the current state, as well as an action I take. So the sort of the kind of the agency, so to speak, that this agent has, and its ability to kind of infer which actions to take. And furthermore, E, the prior over policies. I mean that can be learned. That gets incorporated. C, preferences, priors over observations. Those are more often left static. So those are more often left static in the sense that they become a kind of attracting point for particular observations. In that case, that kind of supplies the agent with a sort of goal, a kind of like it's seeking out particular observations that it prefers or expects. In the sort of theoretical literature, the idea is that it relates to the notion of homeostasis. So I prefer to observe my blood oxygen level being at a certain point, or I prefer to not observe my stomach growling because usually it's a sign that I'm hungry and I need to do something about that, which in a that context, it would that C would then inform what I should do via the B matrix of, oh, my stomach growling must mean I'm hungry, and I know that if I eat food, I will no longer be hungry at the next time step, so to speak. Um, so again, any of these can be learned, and I know that there's a nice figure that kind of gets at the point of this, but I don't want to get us too lost in the weeds. Hybrid models. Essentially what happens is that we end up with this kind of hyperparameterization of all of those model components. Okay, I'll stop scrolling around because it might be that we missed that one. It's still relatively new. Uh, so you would have like a prior on D, which itself is in the discrete state space setting. So it would just be like a kind of, so it'd be a Dirichlet distribution. So it would be like a categorical distribution, but the values can in fact exceed one. They don't have to sum to one. You could almost think of it as a kind of like Dirichlet counts system where it's like, oh, I I have my D matrix, but then I've also experienced like more of this state in many more time steps. So it implies that that an agent actually has a history of states and a history of observations that it's kind of accumulated. And then that acts as a kind of hyperparameter on these matrices, which then proceeds to modulate their values. And then learning them itself will involve free energy minimization. I mean, it's just applying another free energy minimization rule. And so like minimizing free energy is sort of the global uh functional or optimization problem here for just about everything. Like inferring states occurs by minimizing variational free energy. Inferring policies heavily relies on minimizing expected free energy, which earlier on in the textbook, I think it's somewhere in the realm of chapters 2 through 4. There's kind of a broad breakdown about those terms. So actually, we should be able to find those. We have the equations as well. Yeah, great. So something we'll notice very quickly between F and G. F is going to be for, again, state inference, which ends up being treated as a separate process, related. But if you were to code this, like if you were to write this in code, you would actually write like separate logics and even executions of state inference versus policy inference. State inference will involve minimizing F, which, without getting too lost in the various ways we can break this down, we could look at it as complexity minus accuracy, which is the sort of classic, machine learning imperative of how do you create a model that can both be generalizable and not excessively complex and overfit, but we need it to be accurate, so we don't want it to heavily underfit either. So the complexity term there is just what is the KL divergence between your posteriors, what you think now, versus your priors, what you thought before. And then you want to also keep accuracy high. So we want to be able to find the expected value of the log of essentially observations given X. So all this is to say each one of these terms, depending on what the sign is in front of them, we'll want to either maximize or minimize. So we'll want to maximize accuracy, right? Because it has a negative sign in front of it. Vice versa for complexity, we actually want to minimize that. Because at the end of the day, we come back to F, we're just trying to minimize that. Similarly for G, but the interesting thing with G is that whenever we look at just the top line, information gain and pragmatic value, we notice that there are negative signs in front of both of them, and we're trying to minimize G. So we actually here want to maximize information gain, meaning the expected value of the KL divergence between sort of your posteriors, what you think now, conditioned on what you've seen and what you've done, and the divergence between that and just what you think now versus are conditioned on what you have done. So this is kind of like saying, oh, now that I have actually observed the outcomes of what I have done and what I believe now, versus simply just relying on, sort of what I've done. It kind of prioritizes this idea of, oh, I need to collect more observations. And I actually want those observations to be quite different from what I'm used to seeing before, what I'm so used to that I can practically sort of marginalize them out, right? So that's sort of the exploratory behavior we see in active inference. And furthermore, just the fact that we have this functional that actually allows for both exploratory behavior and pragmatic value, which is simply your observations conditioned on C. So like I mentioned earlier, C is often used for defining like goals that the agent has. It's kind of like what you expect is what you want, which is what will help you maintain homeostasis, or it's what will help you achieve that goal that you have in the far future, or however you want to look at it, or goal in the immediate future. And so you want your observations to essentially like you want what you see to actually be accurate versus like your priors over observations, right? So that's kind of, I don't know if you're familiar with reinforcement learning, but anything like epsilon greedy behavior or having to like define manual rules, such as like, oh, you should always exploit with a probability of zero point 0.9 and 10% of the time just do something random and see what happens. Instead, this is what it defines exploratory behavior is directly implicated in computing minimizing expected free energy. So that's the claim in the textbook that these sort of naturally balance out, which is not a sentence that really should be said that way, in the sense of you could still have a scenario where a policy is evaluated such that it might not have any information gain at all. It's just the fact that both are computed. And so there is no manual definition here. We're just relying upon minimizing G and these particular equations. I might have gone much more deeply into that, and I hope I didn't miss
No, I
your
really
original
appreciated
question.
that. I liked your explanation about the meaning of those different distributions that you're measuring the Kale divergence. That was very helpful, actually, especially when you were talking about the information gain and the fact that one is conditioned on Y hat or Y tilde and one is not. I just sort of not connected those dots before. So,
Yeah,
um,
yeah, no problem at all. I
and
mean,
can you say again? I think you said it already, but can you say again the difference between P and Q? Is this related to the world model versus the agents model, like the true world
oh,
versus the agents, what's in the agent's head, or is it something else?
yeah, sure, no, good question. So, if we were to kind of use the phrase, is it just in the agent's head or the world? It's all of this would be in the agent's head,
Okay,
right?
okay,
So, yeah, yeah. So, and then, uh, in the sense that like this is the agent's beliefs about states. This is kind of the breakdown of the overall rule of computing free energy over states. So states as in my beliefs about the world, and then G will be used for inferring what policy should I use. So that's as opposed to state inference, it's policy inference, right?
okay.
So the and all of it is in the agent's head, as it were. And then for Q and P, so Q is always used, they always use that to denote posteriors. So this is sort of like what what do I think after a given instance versus and versus what did I think before, right? So
Okay.
there's this kind of model inversion process that happens where we compute F by sort of sorry about this, figuring out our posteriors, figuring out our relative to our priors, and that's what allows us to kind of score the final, like, what is our final belief now that we have all of that and we have now minimized the free energy, right? So
Hmm.
just basically employing Bayesian inference, but in the context of a fuller functional equation. Yeah. Yeah. Yeah, so there are a lot of interesting ways that these terms get broken down, and I know that like for a lot of folks who get involved with the institute and their learners, especially those who are not terribly comfortable with math or probability theory, it's sort of like these things can be very very intimidating, right? To just like quickly see like let us tell you all at once all these different ways you can break down G
Yeah.
whenever you're still trying to learn what this little C is over here and what that means relative to anything else, right? And what's the tilde about, right? So, and I'll also, I guess I'll mention that the tilde is so G, what you're doing here with G and the whole G over pi is you're you're inferring your beliefs about each policy you have available over some inference horizon, which is why we call it expected free energy. It's that it also is variational in the sense of like they're relying on different kinds of, approximate methods, variational methods here. But the expected part is emphasized because if if I notice I'm hungry and I'm trying to decide what to do, it's like, well, if I decide one policy I have is that I need food, there's going to be a series of steps that I'm going to need to take. Do I have food in my fridge? Is it at the store? If it's at, if I decide going to the store is what I want to do, then like, what are the intermediary steps of what I need to do from between now and then? Um, Surely I don't think about every single thing, like the entire process of what it will be like for me to walk down my apartment complex's hallway, but more discreetly, I know that I will need to say stand up, and then I'll need to leave my apartment, and then I'll need to travel or take transit or otherwise to the store, and so on. So it's kind of like the tilde is just acknowledging that this is a sequence. So what are the kind of expectations I have over what will happen if I follow a particular policy and how I think it will occur. So, um, which is why we also don't see the tilde up here, because this is more about moment to moment inference, which again relates back to earlier the point about learning, right? Because that's an important distinction between the two. And active inferences, state inference is just about, in real time. You think about again the musician playing notes in real time, and it's very directly related to their ability to hear the note that they're playing versus what they think it is. So that's one way of kind of just more conceptually conceiving of these things. So uh,
Okay, and so I guess especially with G, it seems to me that the reason you would choose one breakdown over the other, maybe with not just G but all of them, but is because you're trying to figure out what's actually computable, like based on the computing resources you have.
hmm,
Maybe it's a lot easier to compute that fourth line there with the expected energy and entropy than the other options. And in terms of what's actually solvable.
hmm, hmm. That that's possible. I mean, it's never made very explicit why we have all of these different breakdowns. The crucial thing is that like the way the math plays out, it's necessarily the case that this first line, like one version of G is information gain minus negative information gain minus pragmatic values G, it's necessarily going to be equivalent to the value here, um,
Mhm.
given the equation, right? And so it's sort of like now another sort of tricky thing is that this is sort of they will be less than or equal to these other terms. So this allows for almost I don't want to get too abstract and mix things together, but it's almost like this is an additional, like this is the lower excuse me, the upper bound of the upper bound on like expected future surprisal, right? It's because we already know that F from definitions of surprise, like F is just an upper bound on surprise that
Mhm.
works out mathematically. And so it's kind of like saying, well, these are the upper bounds on surprise expected in the future. And these are kind of the upper bound to the upper bound because of this sneaky less than or equal to sign here.
Right.
Um, so so another thing is that it's sort of like the another aspect of this beyond that is the authors try to supply their own definitions of the different ways of breaking these down. And so expected free energy in just about every, it's a broad generalization, but I genuinely think maybe 80% to 90% of all literature you read in active inference, most people are just going to focus on describing it this way, information gain and pragmatic value, because it comes off as the most intuitive and it's also the
Mhm.
most interesting in terms of viewing things in like explore exploit paradigms. It's just this is the clearest way of kind of expressing that. And So it's just intuitive, like, oh yes, I want more information that actually increases like what what I thought before versus what I know now. It's almost like I'm seeking out. I hesitate to use the word learning because of its technical connotation here, but sort of like I want to learn more or I want to find more. It's a sort of a someone who wants to have fun doing something new for the sake of it. I'd sort of think about that as a more colloquial way. And then pragmatic values just, is what I'm seeing or what I expect to see. Is it going to be aligned with my priors? So is this particular action, this particular policy I'm evaluating, like going to the store to get food, is that going to help me achieve observations that match what I want, which is attaining food and kind of watching and myself eat it and then watching my stomach no longer growl is a kind of odd way of saying it, but it's closer to the ideal of how it would work. Yeah. I think part of the breakdowns here is just sort of it's taking into account, so like with expected ambiguity and these other terms, some of them additionally get introduced in chapter 7 as well. Posterior predictive entropy, those kinds of terms. It's kind of like just saying like, oh, it's sort of like this idea that there's a lot of other dynamics of how we could view these playing out. So expected ambiguity is like oh that for example is sort of what is the entropy of what I expect to see versus what I expect will be going on. So if I expect that the it will be light outside because I believe it's daytime, and I expect to see that it's dark outside because I believe that it is nighttime, then it's sort of like we have this nice one-to-one discrete mapping. It's light out, it must be day. It's dark out, it must be night. Um, However, if we if we expect more of a one to many mapping, such as oh, it's light outside, it could be day, or excuse me, it's dark outside, it could be night, or it could be a solar eclipse right now, right? And I'm just not sure which. I didn't pay attention to the news. I don't know like what's going on, right? So that's suddenly where you get more of a one to many mapping between like what could this particular observation mean. Um, and here it's a positive value. So we'd actually want to like minimize that kind of that entropy of that situation, thus the expected ambiguity. Um, and then risk over outcomes. So these risk terms that get related to, because there are a lot of people who go into this field not just because they're interested in, say, neuroscience, but they might be interested in other fields. I myself have a background in I did my master's at U Chicago in this very broad social sciences program. That's part of what brought me here, including an interest in economics. So looking at risk. And so this is like your posteriors versus your priors. Like what do you believe right now about what you would expect to see versus pi versus like what do you believe after, right? So what do I expect to kind of see from what I do versus what I'm used to, sort of, and finding the KL divergence between those, right? And you want to minimize that, which is a little different. So it's just there's so many ways to break it down and so many different ways to attempt to put into words why these equations work the way they do. That's sort of the trick, isn't it, of not just active inference, but sort of cognitive and computational modeling in general. Like, well, if we have real data and we have real approximate methods of mapping things like beliefs and actions and inference and learning processes, how do we put into natural language what any of those things mean? So I think it's a fair attempt, and I personally, like many other people, kind of prefer this top one, but it is interesting breaking the rest down. And then it's kind of like the further you go down the line here, we get closer and closer to theoretical physics, which is yet another kind of partner field of active inference, and a lot of Karl Friston and other folks' um, research, right? So just
Yeah.
having energy terms that,
Yeah, my background is in physics, and I think that's a large part of why this appealed to me as a I'm working on a robotics company, so um, that's how came into this and found it, and why I think it attracted me was the analogy to physics, and um, I'm hoping to
yeah,
figure out some ways to reduce the amount of data that it requires to for an agent to learn a task or to decide to do a sequence of motions or something.
yeah, no, absolutely. I mean, it's I don't know if you skipped ahead to chapter 10 in this textbook at any point, but I think they spend some time on robotics and you know the more theoretical aspects of like cybernetic processes and sort of feedback loop operations, but then
Mhm.
like suddenly with active inference and this very broad interdisciplinary aspect, it's sort of like because it can go so many ways. Because it comes out of neuroscience. I mean, one way, one kind of funny takeaway, and maybe it's not funny, but I think it's kind of fun, is like a lot of this relates to the brain and inference processes as well as looking at behavior, like the T-maze example that we get in this textbook. So, you know, like a similarly to actually having a real mouse in a lab, but then if computational psychiatry plays into this a lot, and it's actually like it's a growing field, and many people are trying to cognitively model. And I'm working with a research group here as well. But we're working on creating an active inference model of PTSD actually, and
Mm.
sort of what are the behavioral dynamics there, and sort of the belief dynamics, and can you find a generalizable but still approximate sort of model of these dynamics in relation to neurobiology, and then in future, like being able to kind of fit that model to real empirical data that could be collected from, you know, willing participants who have PTSD.
Hmm.
Um, and all this is to say, the reason why I'm kind of going on about it, despite the fact that we started with robotics, is that it kind of, in an interesting way, it's almost like is a bad machine learning model or a reinforcement learning model, like if it's bad, should we view that as a kind of like like a pathology? Can we view suboptimal behavior as sort of something like pathological behavior? So I just think that's a fascinating kind of take, and I've talked to a few people who are more focused on sort of optimizing models rather than, you know, they're not worried about attending to human beings and modeling that. They're wanting to create very efficient, you know, kind of engineering based, you know, tools and so on. Um,
Right.
and we've always had interesting conversations about that because in active inference, it's like there's a term that's used sometimes. The term is a hyper precise priors, and so that would kind of be like a scenario where, to bring it back a little bit, it could be, for example, a situation where skip it because it's in figures. So, like, imagine an agent, you know, imagine our musician example again. We don't have to even have to worry about policies just yet. Um, Imagine this agent like had a very precise hyperparameter like on their A, like a very strong prior for their A matrix. And for some reason, they're just learning it at either an incredibly slow rate or not at all. And say the A matrix was really biased. So like with the this example, like say the agent was heavily biased to assuming that like if they're both like these beliefs are necessarily like one to one with these, to where even this kind of light gray space didn't appear, so to speak. It's like they wouldn't track the prediction error because they believe in the Bayesian sense so strongly that this is in fact how things work,
Hmm.
perceptually, given that the HMM is just like a perceptual model. Then it's kind of like saying like, oh, that's it in robotics, that, I mean, that would be awful. That means it's not able to like read the data streams in a way that allows it to make any kind of like flexible, adjustable inferences. Instead, it's going to just assume whatever it sees, regardless of what it is, just reconfirms like its beliefs about, what's going on. And if this were a POMDP, then also what it should do in response to the data stream it's receiving.
Hmm.
But simultaneously, the pathology bit is sort of like, oh, that would, for a musician, that would mean that they believe they're really good at music all the time, right? Because they're sorely convinced that their beliefs about what should be heard or what should be played or what's going on necessarily match the incoming data stream. And so the incoming data stream will just kind of like, it won't, the variations in it won't really matter. It's like there will still be a
They
one,
won't
be a
even
one to
hear that
one.
they made a mistake, essentially. They'll
It,
believe that it's right.
exactly. And so not to sound insensitive or phrase this wrongly, but I mean, if you start thinking about things like schizophrenia or psychosis, where something in reality is not going on at all, but the person believes it is, it's like in a certain way, it's they're perceiving reality in a way that's heavily biased by these kind of priors that they're coming to the situation with, right? So you're
Hmm.
sort of stuck in that, if so long as your inference process is kind of, kind of pathological in that way. Um so yeah, it's, I mean, with robotics, that's not my key field, as it were. So I can't say too much, other than anytime I've skimmed it, there's always being something interested being said. And that, with a lot of these models in various areas, they're highly performative, including in when comparing them, let's say, to reinforcement learning, because
Right.
it's another way of looking at active inference, especially POMDPs, or any model that is actually augmented with the capacity for action. We're effectively just looking at, okay, here's an agent who receives observations and infers an action it should take. If we just look at it as a Markov decision-making process, like remove the partially observable part, then it would just kind of be like it's as if they already know what the state is. They observe a state. It's sort of more one-to-one. We don't have this extra observation versus states part,
Right.
right? But nonetheless, I mean, this is still the canonical bit, because I mean, this is, as far as kind of the neuroscience bits go, I mean, we're always in a partially observable environment, right?
Right.
So we don't always know what an observation means, and we haven't even said anything about, like, you know the possibility that the sensory receptor itself is bad, whether it be a person who's nearsighted, and so anything far away is just very hard to see, or it be um, a robot that has a receptor that is just like not functioning correctly, or
Hmm.
um, an EEG headset that, like, someone left the ground, they didn't set that up right. And so it sees really high amplitudes, not because of the person's neural activity, it's because it's getting like supercharged. Um, so in an inaccurate way. So that's sort of the partially observable bit. They do, I mean, anytime I look at model comparisons, it's just, people do very regularly benchmark. Um, yeah, they regularly benchmark these models against reinforcement learning models. Usually, eh, again and again, furnishing an inherent balance of exploration and exploitation. Like, so, So a lot of
Hmm.
people point that out, that they just find a lot more sort of credibility in the notion of like, oh, these agents, because of G, uh, they're sort of naturally, internally, architecturally incentivized to seek out more information. And nonetheless, like once they're affirmed that they have enough information, they are over time more than likely going to become like, oh no, I've seen that before. So that they kind of know not to go necessarily in that direction. However, it's over a policy horizon. So maybe that policy horizon is 5 steps in the future, or in continuous state space, it could be, a minute into the future, and what
Hmm.
they expect to kind of see over along the way. Um, so even if they think they've explored a space well, they might not necessarily know the full sequence of transitions that'll happen over time. So that it's very likely that they'll be able to, depending on your setup, continuously find ways of like getting information gain out of a situation, computing that, like incorporating that into their decision making. But once they become much more reaffirmed that they've explored enough, then they start to, I'm speaking from experience and
What causing nosebleeds?
modeling. Sorry.
Oh, in Monterey Bay.
Oh,
I'm not sure he's talking to us.
no. Here you go. Um, so yeah, I that kind of interrupted my sorry train of thought. But it's just to get to the point. It's like very often than not, I think that T maze example and spending just like an extra, not a long time, but just like a minute or two. Because I know with robotics, you're usually looking at continuous streams, right? I mean, maybe there's
Yeah.
a, I mean, go, sorry, go ahead. Yeah.
Yeah, I was just gonna say yes. What I would love to be able to do is take a 6 degree of freedom robot arm and output the 6 joint variables that are continuous, and between some limits, and that would all be given some sensory input, and then beliefs about what that sensory input indicates about current state.
Yeah.
So,
No, it's incredibly relevant to a lot of the work that is done here. And it's sort of, you know, one way that they break down, if you've looked at the book and become more familiar with the notion of like an observation modality, which is, a very common sensical thing. If you get rid of the jargon, it's just sort of like, I can see things versus feel things versus taste things. Like there are different ways that I can receive information. And so they tend to break those up into 3 different categories. And so there's exteroceptive, which would be like information I receive from the outside, which includes all the things I said earlier, that the sort of common 5 senses of like I can see and touch and feel things. Interoceptive would be like internal bodily signals, that are coming like sort of from within, that I'm not necessarily feeling them in the typical sense of like my skin is in, the sort of dermal aspects. Um, and then there's proprioceptive, and that's if you come across that term, or, and sorry, by the way, I don't mean to sound condescending if you already are familiar with it.
no, no, this is great.
No.
Thank you.
Cool, definitely. Yeah, so proprioceptive, I'm just trying to find it quick, and we might have to wrap up then. Is oh, I know it's in here. Um Somewhere they have a nice sort of visual description of like the idea of like, what's this it? Ah, proprioceptive afferent. So this is still related to more like the brain, but proprioception, you know, it has much more to do with like movement and kind of reactive systems. So there could be like a reflex arc sort of logic, for example. That might be of interest to you if you want a model that's kind of a little bit more complex, or sort of savvy with putting together the architecture in regards to active inference. There's no necessity of it though, and I think you might especially find chapter 8 interesting, which is going to explicitly go over continuous models. It, of course, is different because of the continuous space, like time and continuous state space sort of setup.
Hmm.
Um, but then in that case, we're looking at more like kind of these attracting points, or here this is rather complex, but this is a Lorentz, chaotic system, and sort of like different kinds of dynamics and viewing them in different ways, and viewing how, like I mentioned with the discrete state space setting, there's C, which is sort of defining your goals or your expected observations you want. The sort of equivalent of that in continuous state space models, you could view that as is sort of like an attracting point, or a distribution of attracting points, or an attracting distribution over a continuous space, and just modeling it like that. You'll also it relies a lot more on sort of Taylor series approximations. There's this notion refers to it as the generalized coordinates of motion. So it's sort of like there are these more sort of working more directly and explicitly with derivatives over time. So I realized that actually kind of shot by the time. But thanks for this opportunity to get into to sort of the deeper theoretics, and really honing in on some of these equations.
Yeah.
It's sometimes folks with the here I'll pause. Also, thanks for bearing with the this was my first time ever kind of doing this purely solo, so it was fun. Yeah. So I'll go ahead and stop recording, and thank you everyone, and see you at the next one.